This next discussion we're about to have is a very difficult one. It's on electrons and light. And Richard Feynman, a Nobel Prize winning physicist, is quoted as saying, "It's safe to say no one understands quantum mechanics." So I start this with a little fear and trepidation, but always some excitement, because there are pictures in chemistry that students need to grasp. We've already talked about the atom and how they have different numbers of neutrons in them, the isotopes that you have of certain elements, but that's on the inside. We often need to worry about what's on the outside of the nucleus, because that's where the action is. That's where atoms stick together and make molecules. It's where electrons can be expressed more or less to give us hydrogen bonding, things that are important for the DNA double helical structure. Electrons pretty much set not only the bonding for molecules, but the properties, how they sticky, elastic, how they interact with other molecules. It's all on the outside. So the outside is really important, these electrons. And unfortunately, quantum mechanics does become necessary to describe what's going on with these electrons. So I just want to warn you that the pictures you've been given maybe in high school are good starting points. They're important, but they are a starting point, a foundation to move on up into the 20th century, 1920s, 1930s. And it hasn't really changed too much since then till the 21st century, 2020. We're 100 years past some really important developments. And I'd like to talk about those. This will be cut up into 3 sections. This first one's just to kind of convince you that we need to get rid of the old model, or at least, how they would say, amend it, add to it. So let's get there. First of all, one thing that's going to blow your mind is we know electrons, maybe you think of them as particles, but it turns out that they behave as waves. Waves, not just riding a wave, like a particle on a wave. No, they are the wave. So you're going to hear me say this, whoomp, whoomp. It's like everywhere. The electron is disembodied and is everywhere. But they also still do act like particles. They act as both. Sometimes when you're looking for a particle, it'll act like a particle. And when you're looking for it as a wave, it'll act like a wave. So that's what's so crazy about these subatomic particles, things smaller than an atom, like photons and like electrons. So we use energy diagrams, orbital diagrams, to describe electrons, and we'll use electron configurations to talk about them in text. Now, you may have learned about electron configurations in high school where you had 1s2, 2s2. That's sort of a textual representation of the orbital picture. So we really are going to get to this in the second video. What are the allowed orbits for electrons? And we use a diagram. We'll lay them all out, what orbits are available for electrons to be in. We lay that out through an orbital diagram. That'll be the second video. And then we'll probably spend the third video looking at applying some of that and looking at quantum numbers. Now, it gets really hairy, the math and such, when you get into quantum numbers, but we'll just go through an overview. What are the principal quantum numbers, angular quantum number, magnetic quantum number, things like that. Let's start off then, if we can, with just the first picture that most students learn in high school regarding an electron. So they imagine this nucleus with a positive charge and some electron going around in an orbit, this nucleus, like we would in an orbit of the Earth around the sun. It's called the orbital model. I think it was called the Bohr model of the electron. And if you hit it with electron, or hit it with the light, this electron will get excited up to the second energy state, the second orbit, and then as it relaxes, it'll come down instantaneously and kick off a photon of light. Light is represented by this h nu. So you may have learned about this, that this is the first shell, and it has 2 electrons. The second shell has 8 electrons. That's sort of a simplistic view of the electrons, but it's a starting point. Where we're going to be in this first video is getting to this idea, away from the idea of a particle going round and round, to the idea that the particle is no particle is just a whole wave around the nucleus. Whoom, 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 whoom. It's everywhere. That's a pretty important concept that came in with a French scientist named de Broglie. So let's go back to the very, very beginning of the views of the atom. Of course, Dalton thought it was just one big atom. There was nothing smaller than the atom. There was no electrons, protons, or neutrons. It was just the atom. But we knew, as we started learning more, that the electrons were actually very, very small. There was some particle that was very small coming out of the atoms, and that was Thomson's cathode ray tube. He discovered these small electrons, and so he proposed they were negative charge, and they were inside some pudding, you might say, that is the atom now of positive charge. It's like the dough, and these would be the little raisins of negative charges within the atom. This is called the Thomson plum pudding model. You just need to know this was kind of where we started to break away from Dalton's idea of the atom as being indivisible. That's in 1904. That expanded, though, to what we saw as just the Bohr model on the previous slide, where we have 2 in this sphere, and then 8 in this orbit, and 18 in the next orbit. Things that I think high schoolers have heard of. Maybe it's just been a while since you remember it. And then you'll hear sometimes that they'll drop down in energy or go up in energy, jumping from one level to the other. That's called the Bohr model. It caused a lot of, I guess, consternation, though. It's known that if electrons change its momentum as it goes round and round in this field, that they should cascade and all fall into the nucleus. It should lose energy. They should just like a fading star, they should emit a lot of energy and then just annihilate each other here in the nucleus. But it didn't. Data just kept coming back and back that there would be some indications that there's only, when you excite these electrons, that kick off energy of a certain wavelength or of another wavelength. They had, it seemed, certain shells that they existed in. So in 1913, Bohr said, I don't care about the current theories of electrons. They seem to be in particular orbits around the nucleus. This is where many got again upset and didn't know what to do, but de Broglie proposed this. In 1924, he said, well, what if the reason they don't fall in, so to speak, is because they're not exactly particles. Maybe they are a little bit of a wave. And as you know, a wave can't be expressed in one spot. So he thought there's some sort of standing wave. So you can imagine this sort of oscillating and breathing almost. This wave around the nucleus in space and time has to be expressed. It can't come down anymore. There's only some lowest energy wave that this can be, I guess, exist in. So it's a wave. It's just all woomph, woomph there. That's mind-blowing. This idea that electrons behave as waves. But it was something that Albert Einstein actually reviewed his paper, his PhD thesis, which what you have to write if you want to get a PhD. The folks that were on his board said, let's give it to Albert Einstein, and Albert Einstein kind of blessed it and said, yeah, this guy is on to something. He's explaining what might, I guess, be the reason why we don't see this electron just collapse on itself. Maybe there's something to it. And it's not a bad idea. So what I'd maybe like to try to do on another piece of paper to explain this is we know that if you take 2 walls and you take a slinky, let's say, and you start putting energy into it, it can express itself like in certain sort of waves, standing waves. So you can imagine if you're here and I'm over here and we're holding that slinky can start to go up and down, oscillate, where it doesn't have a node. But if we sort of rattle it a little faster, we can get a higher energy wave where now we get oscillation around this node, and we would say that's an allowed wave. Now again, if you don't confine or hold on to this slinky at these 2 points, you can't establish these nice, I guess, waves that keep increasing in energy, and that is a terrible wave. Let's try that again. So now you could say, well, if we had 3 oscillations where this one's going up, this is going down, this was going down, and you could have even higher energy. Well, these would be particular energy waves. So I really want you to take this idea and say, what if we then just, again, this is a wave. We're thinking of electron is like everywhere, all in this wave is the electron. And you just wrap it around the nucleus. There's a reason why this would happen is because we don't have necessarily, of course, we're not holding on to any electron and saying or defining where it has to be, but positive charges of the nucleus are very, very strongly attracting that negative charge. So it's not just a wave property that's important, but it's a confining of the wave. So you can imagine, like we were saying, we took those 2 points of the wave, let's say these 2 points, I'm grabbing them and I'm going to wrap them around because the wave had to come back on itself. It couldn't just go anywhere at once. It had to be around the nucleus. So for 2 reasons we see particular energies that we saw in Bohr's model. 1, the electron behaves as a wave. And 2, it's confined. It has to come back to this same point and going in the same direction, the wave expression. It has to have what we call a standing wave property. You couldn't have you couldn't have just any wave. It had to be particular waves around the nucleus. And that's expressed here. So we can have wave where we have 2 nodes here, 2 nodes here, and 2 nodes here. But now we go even more to 1, 2, 3, 4, 5, 6, 7, 8. So this would be a lower energy wave. This would be a higher energy wave. And we can keep on going with this idea so that we go up in more energy waves, but we have to go in certain chunks. You can't have half a wave. It has to come back and be what's called standing. For example, this wave would be forbidden. When we come back, it has to meet at this point. So this would not be allowed, this particular wave. With that idea, let's just jump then with de Broglie's model and say, well, those weren't the exact waves. It was just his idea that maybe there are standing waves that these electrons have to occupy, but I don't know what they look like. Well, now we do. We have a pretty good idea that the energies, or the waves, the orbitals look something like this. You may have heard of it as a p orbital. P orbitals have a sort of dumbbell look, one side and then opposite 180 degrees. But they also have this color. And it's much like then, if you were to, I guess let me put it right underneath, you can think of it as that wave where we had a node in the middle, and this can oscillate up and down. This is a crest and this is a trough. So you can have that kind of expression. We can also, so that's called a p wave orbital. This one is a d orbital. This is an f orbital. So I can have, if you were to go around, crest, trough, crest, trough, crest, trough. That's the wave nature. But here it's going to be much faster. Crest, trough, crest, trough, crest, trough, crest, trough. That's even going to be faster here. So in closing on this video, I hope I'm kind of giving you some ideas on how we can explain certain energies of electrons. 1, they're waves, or at least they behave as them. And 2, they're confined around the nucleus. So we start to get these particular waves or shapes that electrons are said to be in. And their energies go up from P to D and F, and I didn't even show the S one, which is just a sphere. It would be kind of like that wave that has no nodes, that wave that just goes up and down that we had with our slinky. And in closing, I guess again I want to reiterate, we have these certain energies of electrons because they behave as waves. Electrons behave as waves, and they are, yes, confined. All right, I'll have the next video talking about the particular orbitals that we need to consider, or the waves that we fill with electrons, and then we'll look at quantum numbers. Bye-bye.